Okay, so let's evaluate an improper integral 1 to infinity natural log of x over x squared dx. So first of all, what we're going to want to do is we're going to write this integral as a limit. So I'm going to write the integral, instead of going from 1 to infinity, I'm just going to go from 1 to b, and then I'm going to take the limit of that integral as b goes to infinity. So first thing I want to do is I want to see if I can evaluate this integral from 1 to b. Well, I'm not going to show you that here, but let me just tell you that if you integrate natural log of x over x squared by parts, you'll actually get this result here. So you get minus the natural log of x over x minus 1 over x. And so if we evaluate, I guess you could combine those two as a single minus natural log of x minus 1 all over x. But anyway, so we're going to evaluate that from 1 to b using the fundamental theorem of calculus. So right now I'm just going to carry the limit notation along for now. So now let me apply the fundamental theorem of calculus. So I would first evaluate this function at b, so I'd get minus natural log of b over b minus 1 over b. And then I subtract this function evaluated at 1. So I would subtract minus natural log of 1 over 1 and then minus 1 over 1. Well, the natural log of 1 is 0. So really, when you subtract this, you're really just going to get minus negative 1. So minus negative 1 is going to give you plus 1. So you're going to get these two terms and then plus 1 with them. So that would give you this. Okay. Now, I carried that limit process along with the integrals, but you can just evaluate the integral, then apply the limit. So I'll do that in the next example. But let me finish this. So now I need to take the limit of this as b goes to infinity. Okay, well, let me break this up into the limit of each of these three terms. So I have the limit of the first term minus the limit of the second term, and then plus the limit of 1. Well, this is actually natural log of b over b. That's actually an indeterminate form. That's going to be infinity over infinity as b goes to infinity. So I'm going to apply L'Hopital's rule. So I'll take the derivative of the top, which is 1 over b, and the derivative of the bottom, which is just going to be 1. Okay, because I'm treating b like it's a variable. So that would give me 1 over b over 1. And then if you take the limit of that, you're actually going to get 0. So if you take the limit of this as b goes to infinity, you're going to get 0 here. Now I had already evaluated these other two limits. The limit of 1 over b as b goes to infinity, that's going to be 0. And then of course the limit of 1 is just 1. So 0 minus 0 plus 1 is 1. So the improper integral actually does converge to the value 1. Okay, now this one I'll go ahead and just evaluate this first. So this one, 1 over square root of x from 1 to infinity. So let's just go ahead and write that as 1 to b, and then 1 over square root of x dx. Well, that's 1 over square root of x is x to the negative 1/2. And so when you integrate x to the negative 1/2 using the power rule, you'll actually get 2x to the 1/2. And since we're evaluating this from 1 to b, well, if I evaluate this at b, I just get 2 times the square root of b. And then if I evaluate it at 1, I just get 2, so I get 2 times the square root of b minus 2. Now then I want to take the limit of this as b goes to infinity. But this won't converge, because if I take the limit of this as b goes to infinity, I'll actually get 2 times infinity, which is infinity, minus 2, and infinity minus 2 is infinity. So this integral doesn't actually converge to a value. Now, if you do this one, you can do this one as a practice problem. Do it just like I did this one, and you'll find that this one actually does converge, and it converges to 1/3. Okay, so let's see what I've got here next here. So actually, the previous property, they lead us to the following. If you try to integrate 1 over x to the p dx, where p is a positive number, then if you try to evaluate the integral from 1 to p, 1 over x to the, try to evaluate the integral from 1 to infinity, 1 over x to the p, then that will converge to 1 over p minus 1 if p is greater than 1, but it'll diverge if p is less than or equal to 1. Okay, so if you take a look at this, this is 1 over x to the 1/2. So in this case, p was a half, which means that we know that this is going to diverge. But if you look at this one, this is 1 over x to the 4th. So here p is 4, and since p is greater than 1, it's going to converge to 1 over p minus 1. So remember, p is 4, so it's going to converge to 1 over 4 minus 1, which is a third. Okay, so here's another one. So if you wanted to evaluate from 1 to infinity 1 over x to the 3/2, then since the p 3/2 is greater than 1, then that will converge to 1 over 3/2 minus 1, which is 1 over a half, which is 2. If you have 1 over x to the 5th from 1 to infinity, then again 5 is greater than 1, so that would converge to 1 over 5 minus 1, which is a 4th. And this one, 1 over x to the 2/3 integrated from 1 to infinity, that was going to diverge because 2/3 is actually less than 1. Okay, so now let's take a look at another example. This time the lower limit has the infinity. So I'm going to integrate from negative infinity to 0. So basically, let's go ahead and say this. If we integrate this, it would be the same as integrating 1 minus x to the negative 1/2 dx. And when we integrate that, we get minus 2 times 1 minus x to the positive 1/2. So then, basically what I'm going to do is I'm going to evaluate this integral. Instead of from minus infinity to 0, I'm going to evaluate it from a to 0. And so, since I know that this integrates to minus 2 times the square root of 1 minus x, then I'm just going to evaluate that from a to 0. And if you evaluate this at 0, you get minus 2. And so there's the minus 2. And if you evaluate this at a, you actually get minus a minus, so I get minus a minus 2 times the square root of 1 minus a, so that would be plus 2 times the square root of 1 minus a. Now then I take the limit of that as a goes to negative infinity. Well, as a goes to negative infinity, this term is actually going to go to infinity, and so I'm going to get minus 2 plus infinity, which is actually infinity. Okay, so now let's look at a double improper integral. So let's say I want to integrate 1 over 1 plus x squared from minus infinity to infinity. Well, let's just pick a number between minus infinity to infinity. So you can pick any number, but I'll go ahead and choose 0. So I'll break this up into the integral minus infinity to 0 plus the integral 0 to infinity of the same function. Now I'm going to evaluate these separately. So to evaluate the minus infinity to 0, I'm actually going to take the limit as a goes to negative infinity of the integral from a to 0. See, I replaced the minus infinity with a, from a to 0. Now, if you integrate 1 over 1 plus x squared, that's just the arctan of x. So I need to evaluate the arctan of x from a to 0. Well, evaluate the arctan of 0, so I'd have the arctan of 0 minus the arctan of a. And now the arctan of 0 would be 0, and then the arctan of a evaluate at negative infinity. So as a goes to negative infinity, the arctan of negative infinity is actually negative pi over 2. So this is going to be 0 minus negative pi over 2, which is going to be positive pi over 2. And then if you evaluate from 0 to infinity, well, then you evaluate the integral from 0 to b and then take the limit as b goes to infinity. And you're still going to get arctan for the function, but this time you're going to get arctan from 0 to b. And so if you evaluate this at b, you get arctan of b minus arctan of 0. And so if you take the limit of this as b goes to infinity, you're going to get pi over 2. And then, of course, the arctan of 0 is going to be 0. So you get pi over 2 minus 0, which is pi over 2. And now we have to just add the two together. Pi over 2 plus pi over 2 is simply going to give me pi. So that's how you handle those when they're doubly improper. So I'll shut this video down here, and then I'll pick up on the next video, and we'll talk about infinite integrands.